Good evening. Good evening, everybody. Am I audible? Hello. Yeah, good evening. So let's get started. So good evening once again, guys. I hope we just started the refrigerant study, and we in the prayer sessions just pursued some important topics regarding the refrigerants, uh, such as to be the specific heat and the critical pressures, critical temperature, and the thermal conductivity. So, and after that, just again started over the remaining refrigerant study itself, such as the base classification, which is primary refrigerant and secondary refrigerant. Among the primary refrigerants, we hopped over to this ammonia and carbon dioxide, and similarly, there's hydrocarbons. And typically, I already explained the refrigerant abbreviations given to those individual substance itself. For example, ammonia is also called as R717, and whereas carbon dioxide is also termed as R744. Okay, and again, we just completed the study of synthetic refrigerants such as CFC compounds, HCFC compounds, HFC compounds, and these and exceptionally we studied about the important factors according to the ODP factor and GWP factor, isn't it? So, so this is the things that we peaked in the last few sessions, and whatsoever among this CFC and HCFC and HFC compounds, we discussed about a lot of replacements that we've been introduced, isn't it? Like from R1 to R11 to R32. R11 is replaced by R22, and R22 is replaced by R32. So typically, the implementation of this HFC compounds mainly rooted based on the ODP consideration itself. So we studied that for this HFC compounds, the ODP factor should be zero. That's what we actually want while choosing a good refrigerant, isn't it? So these are the points that we've been studied in the few last session. So remaining on to that topic itself, once again, it's about the blends. Okay. So what do you mean by blends? Typically, blends mean some kind of mixture which having one or more number of substances. So that's what do you mean by blends? Generally, there are two kind of blends are there, which is azeotropic blends and zeotropic blends. Okay. Whereas in the case of azeotropic blends, here, if you are mixing some kind of compounds, uh, like one or more amount of compounds, and made it has to be a mixture, then during the refrigeration cycle, these entire mixture will work as a single refrigerant itself. That means even though it is a mixture, but during the working, it should be act as a single refrigerant. Or in other words, we can elucidate it has to be these substances or these individual substances having a more common boiling points. Okay, so that's what the reason it should be considered as an azeotropic blend. Okay, so azeotropic refrigerants are blends which is made up of two or more refrigerants, and that they have the same equilibrium vapor and liquid state, or same equilibrium vapor and liquid phase compositions. Okay, that means on a certain temperature, the entire mixture will act as a liquid. On another certain temperature, that should be act as a vapor. So that's how these azeotropic blends will work. Okay. And here, more simply stated, the refrigerant blend behaves as one refrigerant. That's what I told you right now itself, isn't it? And it does not fractionate. Fractionate means, it should be sedimented as a different components across the work. But these azeotropic blends will sorry, it does not like that way itself. It is always meant to be in a common state. That means it will entirely act as a single common refrigerant right there itself. So basically, azeotropic blends are named as or segregated in 500 series. Okay, that means R500, R502, R50, 500A. So a lot of blends are there. So especially azeotropic blends are named as in the under R500 series. That's it. Okay. So as per the ASHRAE standard 34, these designation goes to R500 series. That's it. Or 500 series typically meant to be azeotropic blends. Then next of all, it's about zeotropic blends. Okay. So in zeotropic blends, you can see that, yeah. Okay, fine. In zeotropic blends, here, even after the mixing, the properties of both refrigerants will remain separate. That means here, these blends that change their volumetric composition and saturation temperature as they boil. Or in other words, these substances will have two different boiling points or multiple boiling points. That means they will typically fractionate right inside the working itself. Okay. So is it clear, guys? So that is the concept of zeotropic blends. In the case of azeotropic blends, they having a common saturation point and common equilibrium for vapor and liquid composition itself. Whereas in the case of for zeotropic blends, it doesn't work like that. Even after the mixing, they will definitely fractionate. Okay. Generally, these zeotropic blends are comes under the designation like we yeah, it's like 400 series. Generally, these zeotropic blends are named as to be 400 series. So you know this R410A, R407C, R409A, R401A, R403A. Lot of refrigerants are there, and the most common type, the most widely used kind of refrigerants are R410A and R407C. Okay, so how these R407C is uh, synthesized? You know, R407C is synthesized by the mixing of R32, R125, and R134 at a certain composition, like a weight ratio will be there. That is like 23% of R32 and 25% of R125 and 52% of R134. So this is the weight ratio between the mixing. All right. Generally, this R407C can be dropped into an existing R22 refrigeration system itself, which means if a compressor works on a R22 based refrigerant, we can replace that R22 refrigerant with these R407C itself. That means initially I told you guys each and every compressors should be allocated for different kind of refrigerants. Okay. For example, if a compressor works on R22 and you are in the same compressor, you are filling R134A, maybe that does not will get worked properly or the expected refrigeration effect will not be there. Okay. So that's why here I told here that I mentioned right now itself. So generally, in the case of R22 based systems, you can actually implement R407C as a in the same existing mission itself. Okay, clear? So these R407C is being used in many applications, and clearly the performance can be improved with minor changes to the refrigeration system. That means adding some condensers. You know, generally, if you are adapting this R407C into an existing R22 system, you know, small minor changes must be implemented. So, however, it's not possibly we are not doing right inside our systems itself. Then once again, guys, here the ODP factor for R407C is again 0 itself. Why? Because I told you the mixing is R32, R125, R134. The entire mixtures are typically an HFC compounds. That means they also having 0 ODP factor, isn't it? So that's it. Next of all, it's about the synthesization of R410. R410 is a zeotropic blend itself, whereas you will be mixing R32 and R125. Okay, so this is R32 and R125. Here it's having minimal glides. So minimal glide, which means it's nothing but, guys, uh, typically these R410A can operate at higher pressure than that of R22. So yesterday I told you guys the other refrigerants are always competing with R22 itself, isn't it? So in the case of an R410 air-based refrigerant, these refrigerants having higher compression or higher operating pressure than that of R22 itself. And these R410A can be used as a new generation replacement for R22. That means for small scale application. Nowadays, these compressor manufacturers are started to implement R410 based compressors for residential side applications. That means high wall AC, similarly like that. Okay. So this is the idea of R410A. Then the one problem with the R410A, whether if you having a high ambient, that means the atmospheric temperature is too high, then you can't prefer R410A as to be an air cooled method. Okay, that means due to high ambience, you can't use an air cooled condenser to cool down the R410A. Instead of that, you definitely need to provide a water cooled based condenser right there itself. Okay, clear? So this is the concept of R410A. Generally, you know, while charging, what do you mean by charging? Charging is the process of filling refrigerants inside the system. That's it. So while this charging process, typically, if, uh, for example, you having an AC machine which is filled with R22, so obviously what you need to, and eventually, like after years, gradually the gas right inside the system started to uh, demineralize, which means, eventually it may get, what do you call that process? End up in a little bit quantities, isn't it? So at that time, we must need to uh, refill it again, isn't it? We must need to refill the gas again along with the existing R22 itself. So what we will do, we simply purchase a a cylinder of gas, and it should be filled into the system again. That's for normal technician, isn't it? But whereas in the case of you are using a blend, especially in azeotropic or zeotropic, however, if the quantity is even 100 gram lesser than that of the normal situation, it is not advised to refill it again. Instead of that, you need to entirely discharge the gas right from the system, and you need to fill the gas again in a proper manner, which means, if you refill it again along with the existing gas, what will happen? Eventually the mixing composition will differ, isn't it? So that's why it should be advised, especially for the blends, to charge the refrigerant, even if it is a little bit quantity is required, even though it should be advised to discharge the entire refrigerant and then to charge it again initially. Okay, that's how these blends are filled right inside the systems. Okay, clear now. And I mentioned about this R500, isn't it? Generally, R500 is used for low temperature applications. That means, typically this 507C, it is used for low temperature refrigeration. And this R22 is used for air conditioning and chillers itself. And this R500, okay, R500 is used as a humidifier, okay. R500 is used as some kind of, that means that refrigerant should be used for some kind of humidifier working, okay. Then 502 is again for low temperature refrigeration itself. Low temperature refrigeration doesn't mean to be some kind of air conditioning, guys. It's preferably for some kind of cold room conditions itself. Then the other one is R23 is there. Not saying about R22. It is R23. R23 is preferably used in ultra low temperature refrigeration. That like minus 40, minus 30, something like that. Okay, clear now. So this is the general idea of this blends itself. So typically, we studied about natural refrigerants, synthetic refrigerants, and blends. And these three are the subclassification of primary refrigerants. Next of all, we are going to study about secondary refrigerants. So as I mentioned before, secondary refrigerants are implemented right inside a chiller system. Generally, the secondary refrigerants that we are using is water, air, and brines. Okay. So technically, water can be used as a secondary refrigerant, and it is more cost efficient and it is abundantly available in the earth itself. And once again, the refrigerant name of water is R718. Okay, R718 means refrigerant name of water. And for air, the refrigerant name is R729. Okay, for air, the refrigerant name is R729. Then these kind of brines. So what do you mean by brines? Brine is a solution where you will be mixing water along with ethyl glycol. Okay, so that you mean that's what it is called as to be a brine. Generally, brines are used preferably for some kind of sub-zero application, and these secondary refrigerant piping will goes like a long distance. So that's why we are preferring, first of all, secondary refrigerants. Clear? That means if you need a long distance refrigeration effect and long distance travel of these refrigerants, then we will not be prefer primary refrigerants. Instead of that, we will go for something like a secondary refrigerants, like water or brines. Okay. So especially in ice factories, you can see this kind of brines. All right. So this is about the secondary refrigerant study itself. So I hope this refrigerant topic is clear, isn't it? Hello, is it clear, guys? Hello. Okay, le. Hello, am I audible? Hello. Is all good? All right. ഹലോ പുരിയുതാ உங்களுக்கு ഇത് വரைக்கும் എടുത്തത്
ഓക്കെയാണ് ഓക്കെയാണ്
ഓക്കെ ആണോ ഓക്കെ ഓക്കെ മനസ്സിലായി ഓക്കെ ഫൈൻ can we get common refrigerant list with application? Yeah, I will share this PPTs here at the end of this class. Okay. If you ask to Mr. Nasif, he will guide you. So he will intimidate me whether it's I can share those things or not. Okay. You can directly ask him. Generally, you must need to study the basic refrigerants such as R32, R410, R407C, and then even this kind of R500, R503, 502, and typically this R23. So basically for air conditioning purpose, we will be using R407C, R410A, R32, R22, R134A. That's it. That is the existing thing itself. Okay. R22 application means what? Like R20, guys, first of all, R22, R32 doesn't means to be for certain applications. Typically, the primary objective is to do to deliver this heat across the system itself. That's it. That's the first application of each and every refrigerant. Rather than according to their characteristics, you will be choosing the application range. That's it. Okay. Whether it's having much more lesser boiling points and freezing points, you can use something for like a ultra low temperature, as I mentioned in the case of R500, isn't it? That's like that. Okay. So is this is clear? Fine. Next of all, we are going to starting over the machine study itself. Okay. Machine study. So generally in air conditioning, the air conditioning systems are classified into typically two, which is non-centralized systems and centralized systems. So now we can see the differences or not differences, comparison between this non-centralized machine and centralized machine. Okay. Generally, in the case of non-centralized machine, you can see right here itself, the machine size should be small, machine cost should be low, project cost should be low, and as the thing that itself, the coverage area also should be small. That means area of coverage, or in other words, the air throw length also should be comparatively lesser. Okay. Then for a larger application, often you will be need multiple machines. Okay. Often multiple number of machines are required for a larger project itself. But whereas in the case of centralized machines, the machine size is big, machine cost also high, and the project also should be the project cost also should be high, and at the same time, the coverage area should be large. That means only one or two machines are required, like one or very low number of machines are required for a large based project or a large application. So this is the primary difference between non-centralized machines and centralized machines. Now we are going to study about each and every system, every machines or equipments right inside this both classification. So let me again start with the non-centralized machine itself. Yeah. So in non-centralized machines, it is classified it as to be window AC, and the next classification is split AC. So among these split AC, you can see this high wall split, then cassette split AC, concealed split AC, and vertical tower split AC. So this is the four types of split air conditioners that we can see right inside the non-centralized machines itself. So there should be two type of systems, which is two types of equipments, which is window AC and split AC. Among the split AC, these are the four types that you can purchase uh, with respect to the name of split AC. Okay, that's it. Now I'm going to explain about the characteristics of a window AC. So this is how a window AC should looks like. You can see this. I think obviously you've been seeing this kind of machines, especially in your homes or wherever else, whatever. So this picture is a side view of that entire equipment or that window AC itself. Each and every air conditioning machine works on the same principle, which is what? VCR cycle itself, isn't it? That means the same VCR cycle components will be there right inside the machines also. You'll be having a compressor and a condenser and an expansion valve and an evaporator. Okay, so these are the primary and the basic elements right inside a window AC or whatever AC, whatever air conditioning machines, you can see this whole kind of things right there also. Okay, so the working of VCR cycle from the compressor, you should be getting a superheated vapor refrigerant with high temperature and high pressure, and it should be deliberately passed over to the condenser side. So on the condenser side, you know, the atmospheric air should be getting contacted with those condensers coil itself. That's why these condenser and this compressor arrangement should be placed outside of the room itself, isn't it? Or in other words, it's always should be protruded outwards. And you've been seen in your homes, it has to be second. Yeah. So in your homes, you can see this now. Some kind of supportings will be there, isn't it? Some kind of supportings will be there, which holds the backside of the machine like this way, isn't it? So this is how this window AC supports will looks like. And this back portion should be always contacted with atmosphere itself. So that's how the heat exchange takes place between atmospheric air and this condenser coil. Then, after getting a subcooling process, it should be converted to uh, high pressure liquid. And these high pressure liquid should be passed over to expansion valve. So, or the throttling device. Generally, in the case of an window AC, here you will not be having this kind of expansion valve. Instead of that, here you will be having some kind of capillary tubes. So why? Because I told you this window AC is meant to be a conventional type machine itself. Or in other words, this is the starting machine, or this is the first machine that should be implemented as to be a modern AC itself. Okay, now. So in these machines, you can only see some kind of capillary tubes itself. So before this capillary tube, you will be having a small arrangement called as to be a strainer. Okay, what is it? A strainer will be there. The purpose of strainer is to sieve out the small dust or small kind of rust particles along with the fluid. Okay. Why? Because this capillary tubes having a diameter ranging from 0.3 mm to 0.5 mm to 3 mm itself, isn't it? So if the dust started to enter into the capillary tube, a small clogging will happen right inside the capillary tube itself. In order to prevent that, we must need to implement these kind of strainers right in front of the expansion, like right behind the expansion valve itself. All right. Then we know after crossing this capillary tube, due to the friction, the pressure should be dropped and the temperature also should be dropped. And these cold liquid refrigerant should be deliberately passed over to the evaporator side, which is installed, or which the evaporator should be implemented on the front side of the machine. That means the front side is always grounded onto the room side itself, isn't it? So fair enough, these evaporator coil should be arranged like this way itself. And it should be again connected to the compressor. Now you can see a small partition is, a small partition is made in between them, isn't it? And this partition is meant to be nothing but, this is a thermal partition. So why we need this kind of thermal partition? We know this compressor and this condenser having high pressure and high temperature, isn't it? That means, in other hand, the evaporator side is comparatively low pressure and low temperature. So as per the natural law, a normal conduction or convection will takes place. That means a heat exchange will triggered right in between them, isn't it? So if that heat exchange triggers, what will happen? You will not be getting a proper refrigerational effect, isn't it? So that's why we will be choosing, or that's why we are implementing these kind of thermal partition in between them. Then at the same time, you can see some kind of hatched ends on the front side. So this is meant to be the air filter. Okay. This is meant to be the air filter. Then in other hand, you can see something named as M, isn't it? M stands for motor. So a small motor should be connected to a certain fans at both end itself. So at the evaporator side, these fans are called as to be centrifugal fan. Whereas in the case of condenser side, it should be called as axial fan. Okay. So the purpose of centrifugal fan is to blow the cold air along to the room itself. We know, guys, actually a small heat exchange will take place between the evaporator coil and room air, isn't it? So in order to push more air towards the room in a certain manner, we will be implementing these centrifugal blower fans. Okay. Then at the other end, you can see on the condenser side, we've been placed an axial fan. Okay. So this axial fan will throw the hot air to the atmosphere again. And so this is the concept of both axial fan and centrifugal fan. Just imagine, guys, if there is no axial fan, the refrigerant right inside the condenser coil will be getting cooled or not. Hello? Is my question is clear? If there is no axial fan is placed on the condenser side, is the refrigerant will convert from vapor to liquid? Tell me.
It will get converted.
Sorry? Sorry, I didn't get you.
It will, when it is contacting with the atmospheric air, it will get converted. But this fan will help to remove the heat, I believe.
Actually, you are just, let's consider, I'm taking two hot teacups. Okay. Then one teacup is placed in front of a fan and the other teacup is placed on the other side itself, and there is no fan in that area itself. So whatever, after a certain interval, like after 2 minutes, which teacup will having lesser temperature? Which teacup will having the lesser temperature, guys? The one who is in front of the fan itself, isn't it? Am I right? So that is the same concept here itself. But in the same thing, sorry, in the same hand, the other teacup will also having lesser temperature compared to the initial temperature, isn't it? So the point is very simple. Actually, the fan is boosting the heat transfer. That is the sole purpose of a fan. All right. Is it clear, guys? If you are not implementing a fan, sorry, if you are not installing a fan on the condenser side, there shouldn't be a problem. But it takes more time to reach the subcooling temperatures or the subcooling process. Or we can say it takes more time to reach that critical point to let's get it to converted, isn't it? Am I right? So that's why we need an axial fan. So this axial fan can boost up the process, and these refrigeration effect cannot be hindered if there is an axial fan will be there. Guys, actually in the condenser side, if the any fault should be faced on the axial fan side, you can see the machine will not be work properly, isn't it? In other words, you will not be getting the cold air right inside the rooms if the fan is not working on the outdoor unit. You've been seeing that scenarios, isn't it? So here, typically an axial fan is important as like an condenser coil itself. Okay, now it's but the purpose is to boost up the heat exchange process. That's it. Then just imagine, guys. Now let's consider I'm just swapping the centrifugal fan to the condenser side and the axial fan to the evaporator side. Is there any fluctuation will happen inside the working? Tell me, guys, is there any fluctuation will happen inside the working? Hello? Hello? Is my question is clear? If I'm swapping this centrifugal fan to the condenser side and the axial fan to the evaporator side, is there any fluctuation of work will happens or not? That's what I'm asking. You know, the purpose of an axial fan is to cover more area. Okay. Whereas in the case of centrifugal fan, the purpose is to throw the air to a certain distance. So this is why, because at the condenser side, the air is hot air, isn't it? Hot air means it's having less density. But whereas in the case of evaporator side, you will be getting in cold air format itself. Cold air means it's having high density, isn't it? So if you swap this axial fan right in front of this evaporator, your room will not be getting cooled properly. Or in other words, the air will not reach the extent of your room itself. Why? Because it's only getting, it means it's simply pushing the air in a certain or in a slow manner itself, isn't it? But, but typically on the evaporator side, we need more throw. For that, you need more push to the cold air to those rooms itself. But you don't require the same pushing on the condenser side. Why? Because there should be you having low density air, isn't it? That is the hot air. So you can concentrate on onto the contact area itself, isn't it? That means you can see the difference. Why? Because always the axial fan should be much bigger than that of a blower fan itself, isn't it? Actually, this axial fans are preferred as to be propeller type fans. Okay, now, however, we will be going to study the different kind of fans in the upcoming sessions. So this is the idea behind this placing of axial fan and centrifugal fan right inside the system itself. So is it clear, guys? Okay, I hope so. We get the point. Next of all, it's about the machine side. So here you can see which should be the supply side. First of all, if you consider a machine, you need to check the very basic two things, which is the supply side and the return side. Supply side, which means the portion where the cold air should be rejected to the room. Whereas the return air path, which means this the area where the room air which will enters the machine. So typically inside this window ACs, not also in window AC, always the lesser area is preferred as to be the supply air side, whereas the higher area should be preferred as the return air path itself. That means in this picture, this should be the supply air side and this side should be the return air side. That's why we just installed our air filters right in front of the machine. So you know the working. As of the centrifugal blower fan started to throw the air right inside to the room, at the same time, the existing air, the existing air contains hot air and some kind of moisture, isn't it? That's what this existing air will have. Okay. So typically, the existing air right inside the room will be having hot air along with some kind of moisture content. So this air is again pumped right inside to the uh, inside of the machine. Actually, why we require a lesser area? So for that one, you've been studied about this equation, isn't it? Okay, it's not writing itself. Huh? Okay, 1 second, guys. Okay, so you know this equation Q equal to AV, that is flow rate of air is equal to area into velocity. We know, guys, actually the outletting air, sorry, the amount of the air should be pushed to the room is same to the return air. That means the air will be getting again contacted right inside to the machine side itself, isn't it? So in other words, we can simply state it as Q supply is equal to Q return, isn't it? Q supply is equal to Q return. That means we can symbolize this as to be area of supply and velocity of supply is equal to area of area of return and velocity of return. So always the velocity of the supplier should be high, isn't it? That's why we are preferring lesser areas on the supply air side itself. But as in the case of this return side, there is no one to push the return air right inside to the machine. That is a natural process. That's why the velocity at the return should be always lesser than that of the supply. That's why we are preferring and higher areas for the return path itself. So is it clear, guys? Is it clear? For example, if you having in your homes, you will be having gardens, isn't it? So you will be using these pipes also, like pipes, hose, isn't it? So if you close the pipe with your finger, what will happen? Not fully closed, partially closed. The water force will increase, the velocity will increase, isn't it? Due to the reduction in area. That's the same concept here itself. If you reduce the area at the supply, the air can displace more distance, isn't it? But whereas in the case of return, we don't need velocities, isn't it? We must need to uh, ensure that the entire air quantity should be again entered into the machine. For that one, we need more area to accommodate the returning air, isn't it? So this is the concept behind this area differences between supply and return. This is the same concept That's why we placed our air filters right in front of this one itself. Okay, now. So the room air will be getting entered into this return path, and you will be having these air filters. So obviously that should be a 10 micron pre-filter will be there. A small filtration will takes place, and eventually this return air. I told you the specification of a return air is meant to be hot and humid. Okay, what is it? Hot and humid. That means moisture content will be there. That's it. So this hot and moisture content air will be getting contacted with the evaporator coil itself. You can see this now. This is the return air part. So it should be again getting contacted with the evaporator coil and again supplied to this side itself. Okay, now. So once this hot and humid air getting contacted with the evaporator coil, the hot air will absorb the coil temperature, and eventually the moisture right inside the return air started to condensate all over the evaporator coil, isn't it? So this is how the dew formation takes place right on top of the surface of evaporator coils. Is it clear, guys? Is it clear? So that's why we requiring some kind of connection called as to the drain pipe connection. So initially you will be having a drain pan. The purpose of drain pan is to collect the drip water comes over from the evaporator coil, and it should be guided to outside of the room itself. Okay, so that's why we implementing these drain pipe connections.
Sir, this larger area of window AC is return. Smaller areas only supply.
Yeah, it should be common for whole machines. Any machines you consider, if you just seen a larger area, that is meant to be the return. Okay,
Return, okay.
clear.
Okay.
There is a
Okay, sir.
proportion between there is a proportion is there, like supply
Mm-hmm.
to return proportion. Supply area should be 40%, return area
Okay.
should be 60%.
Okay, so okay.
Okay, it's
Yeah.
also up. Now I told you now, it's not only for machines but also for air terminals. Okay, actually this is a designing idea. Then we can learn however. So is the
Okay.
window AC is clear? The working is clear. We can see the drain outlet, isn't it? The drain outlet. We can see this now. So how this drain is formed? Once again, the hot existing room air will be having hot and some kind of moisture right inside it, isn't it? And these moisture, when will be getting contacted with the evaporator coil, what will happen? The water vapor started to condensate, isn't it? And that's how you will be getting the drain water from these high wall ACs, this window ACs, like that way. Okay. Clear? Okay. I hope the window AC is clear. Now it's about the technical specification of window AC. Generally, the cooling capacity range of a typical window AC should be lies between from like 0.7, 0.5 ton to 3 ton, 2 ton. That's it. That is the maximum range of manufacturing of this kind of window ACs. And here you need to study about one more thing, which is about the airflow rates. Okay. So generally we studied that in ton of refrigeration, isn't it? 1 ton is typically equivalent to 12,000 BTU per hour of energy itself. Similarly, in the study of air, 1 ton of machine can prepare or it can produce a 300 CFM of air quantity. So how we getting this CFM? That's very simple. We are going to use the same equation, Q equal to AV. So Q equal to AV means flow rate is equal to area into velocity. What is the unit of area? That is feet square, isn't it? That is feet square. So velocity means what? Distance by time. That means here I'm explaining such a way that in imperial units, not in metric unit. Okay, guys? So velocity means displacement by time. Displacement, which means what? Displacement, which means from A to B, that is meant to be the distance. So that's also should be mentioned in feet, isn't it? What is the unit of velocity? Tell me, guys. Meter per second, isn't it? Meter per second. Am I right? So meter per second, meter is a metric unit. Convert the meter into imperial, that is feet. So feet per second, not second. Here in imperial, it should be in minutes. Okay. So the unit of velocity is FPM, which is feet per minute. Now multiply these both values. You will be getting what? Feet cube divided by minute, isn't it? Feet square into feet, which means feet cube. So this is what you mean by CFM or cubic feet per minute. Okay. That means for 1 ton capacity machine, especially for non-centralized machines, it can produce up to 300 to 350 CFM of air. That means in per minute, 300 cubic feet amount of air should be prepared from 1 ton machine. If it is a 2-ton machine, you will be getting 600 CFM. If it is a 3-ton machine, you will be having how much? 900 CFM. So this is how it goes. Clear, guys? Once again, it's only for non-centralized missions. Okay, now. All right. Okay. So that's it. Next, here you can see this is the flow rate relation. What is it? Flow rate relation. Cooling capacity range lies between 0.5 to 2 ton, whereas the flow rate relation lies between for 1 ton, it's like 300 to 350 CFM. Next of all, the air throw length. Generally, for window AC, that means the blower's throw length itself. It's like 10 to 15 feet to the straight and 6 to 7 feet to the sides. Okay. That means 10 to 15 feet to the straight means what? In the straight, you will be getting an air flow around like 10 to 15 feet. But for sideways, you will be getting only 6 to 7. Okay. So this is how it actually works. Then copper pipe connection. Generally, you don't need any copper pipe connection, like external copper pipe connection, as you can see right inside high wall ACs, isn't it? Why? Because first of all, window AC is a single box installation. That means the entire connection is sealed up right inside a single box itself. So you don't need any external connections. Okay. Then the most common type of compressors using for window ACs are reciprocating compressors or rotary vane compressor. Then once again, guys, here it should be a capillary tube. Why? Because I told you it's generally these machines are considered as to be conventional type machines. Okay, now. Next of all, it's about life expectancy of these kind of machines. Generally, window AC is said it has to be like 10 years, 12 years according to the use. Then normally for window ACs, the condenser should be always air cooled. Right? That means it should be always exposed to atmosphere itself. Okay, here there is no kind of water cooled condensers. It is preferred as to be always a air cooled condenser right there itself. So is the window AC concept is clear? Okay, now. All right, guys. Okay, Le. So is there any doubts regarding this window AC? Throw length. Throw length means what? It's very simple, guys. For example, in a room, you are seated in front of an high wall AC. Okay. And the other guys seated at the back side or the back portion of that room itself. So who will get more air? The guy which is in front of that machine itself, isn't it? So if the same amount of air should be reached till at the back side, you must need throw length. That's why we are preferring centrifugal kind blower fans. Okay, centrifugal blower fans are implemented in order to increase the throw length. If you are using an axial fan, you will not be the the guy who seated at the back side of the room will not be getting the same amount of air as you get. Why? Because it doesn't prefers for something like a throw length. Instead of that, for axial fan, its preference is coverage area. That's it. But we don't need coverage area on the evaporator side. isn't it? Because at the evaporator side, you will be getting, or it should, you will be getting, or you should be synthesizing cold air, isn't it? And this cold air should be distributed across to the room evenly. Then only the rooms get cooled properly, isn't it? Okay, now. All right. Clear. Okay. Range. Okay. Yeah. Throw length range. Normally for windows, I told you, no, normally for centrifugal blower fans, according to the capacities for 1-ton machine, the fan should be different. For 2-ton machine, the blower fan spec should be different. So obviously the throw length is generally considered as like 10 to 15 feet straight and 6 to 7 or 6 to 8 feet to the sideways. That's how you explain on both window AC and split ACs, even for high wall. Okay, clear? All right. Next of all, it's about split AC. So what do you mean by split AC? Split, which means, as the name implies, you will be having two separate units. So the one unit which is placed outside the room is termed as to be ODU, and the other one which is placed right inside the room should be termed as IDU. Okay, so ODU and IDU. ODU refers outdoor unit, IDU refers indoor unit. That's it. Okay, now. So what are the elements that you can see right inside an ODU? That's what we are going to see. In an ODU, you can see a compressor and the condenser and maybe an expansion valve. It's an optional thing. If it is a conventional high wall split AC, you can see a capillary tube. If it is a new gen, which means if it is a modern AC, you can see an thermostatic expansion valve right inside the indoor unit itself. Okay, clear? It should be right inside the indoor unit itself. So this is how this expansion valve should be implemented across a conventional machine and a modern machine itself. Okay, then now it's about the working. You know, here also, split AC means what? As I mentioned right now itself, two machines will be there. So the first one is high wall split. High wall, which means here the indoor unit is mounted right on the wall itself, or it is meant to be a wall mounted AC, isn't it? That's why it got its name, high wall. So this is the typical arrangement of an high wall AC right here itself. You can see this now. This is a barrel type centrifugal fan. What is it? It's not condenser, it is a centrifugal. Okay. So this is a barrel type centrifugal fan. And these lines you can see right here itself. Now, these are meant to be the supply louvers. What is it? Louvers. You can see that fins now, that blades, it will controls there. If you turn on the swing mode, it started to move, isn't it? So that is meant to be the louvers, supply louvers. Then this is the air filter side, and this is also the portion you can see the return air path. Okay, you can see this now. This is the return air grill on top of the machine. So this top portion is always named as to be return air grill side, and this is the supply side. So you can see the difference. Always, as I mentioned before, the supply air area should be comparatively lesser than that of return air area, isn't it? Here you can see on the top of the AC machines, especially on high wall ACs, the return air area should be comparatively high rather than that of the supply air area, isn't it? So that is the idea. Then here, as per the VCR cycle working, on the evaporator, you will be getting cold energy, and it should be again transferred to the room with the help of this barrel type centrifugal fan. So this is a barrel type centrifugal fan. So you can see right here itself, one end should be connected with a small motor. And as if the motor started to advances, these barrel type fan also should be rotates according to the speed of the motor right there itself. Then inside this high wall split ACs, how this air is getting replaced again and again. As I mentioned in the window AC itself, the existing room air will be again pumped over through the return air grill, and it getting contacted with the evaporator coil. So here also you can see the drain, isn't it? Drain means what? The actual moisture content right inside the air, when it is getting contacted with the evaporator coil, it started to condensate. So that condensate is termed as to be the drain water. And on the bottom of the machine, especially in the indoor unit, we will be having a drain pan, and this drain pan is attached to the drain pipe connection, and it should be terminated to the outside itself. Okay. Then on the other hand, it's about the ODU. So generally outdoor units are placed where it is always exposed to atmosphere itself, isn't it? Inside the ODU, you can see your compressor, condenser coils, and an axial fan will be there. Okay. Then same time you can see the cablings, connections, supportings. Now in this split AC scenarios, you need an external copper pipe connection. Why? Because evaporator is right inside the room. So we must need to broadback the refrigerant from the evaporator, and then you need to terminate the refrigerant right inside the compressor for the next cycle, isn't it? So in order to connect these both ends, you need some kind of external copper pipe. Okay, so these lines are termed as the suction line. So what do you mean by suction line? The line or the copper pipe connection which should be connected from evaporator to compressor is termed as to be suction line. Then once again, from the condenser, the refrigerant should be again passed over to the expansion valve or either to the evaporator coil, isn't it? In other words, from ODU to IDU connection is termed as to be liquid line. Why? Because the refrigerant is going in a liquid format itself, isn't it? That's why these line is called as to be liquid line. Okay. Generally, the copper piping distance should be ranges from 25 to 30 feet. That means if the indoor unit is placed right inside your room, the outdoor unit must need to place within a 30 feet range door itself. Okay. If you place long beyond, what will happen? The compressor need to suck the refrigerant from long distance. That will eventually kill its efficiency, isn't it? So that's why always these ODU and indoor unit distance should be in between a 25 to 30 feet. And the compressors that we are using right inside these machines should be either rotary vane compressor or scroll compressor. So scroll compressor, which prefers for inverter AC machines. Okay, I told you that day itself. So typically, in order to, if you need an inverter machine, you must have a TXV, that is thermostatic expansion valve right inside the circuit. So according to the load control, the scroll speed also varies. Okay, that's how you cut off the compressor according to the loads. Clear? And the throw length is still same, guys, like 10 to 15 feet, 6 to 7 feet, that's it. So is there any doubts on this high wall AC? No, isn't it? Is it clear? Is it clear, guys? Till this, is it clear? ഹലോ ഹലോ ഗൈസ് ഓക്കെ അല്ലേ എല്ലാവർക്കും മനസ്സിലായോ അത് അഹമ്മദ് ജിഷ്ഫാൻ ഒക്കെ ക്ലിയർ ആണോ compressor types are typically rotary vane compressor or scroll compressor. If you have purchased an inverter AC machine, then the inverter AC machine will be having a scroll compressor normally. Okay, in order to do the load controls. I told you that day itself now while explaining about thermostatic expansion valves. According to the room loads, which means if you having very high temperature right inside the room, a lot of opening will takes place, isn't it? At that time, the compressor need to work full loads. But once the room getting set, reaches the set point levels, the the thermostatic expansion valve started to close, isn't it? That means eventually the refrigerant pumping will be comparatively lower than that of initial levels. That means you can vary the speed right inside the compressor itself. So that's why we are preferring scroll compressor for smoother swapping of the speeds. If rotary vane, you must be having capillary tube. That's it, yeah. Rotary vane നമുക്ക് അങ്ങനെ സ്പീഡ് കൺട്രോൾ ചെയ്യാൻ പറ്റത്തില്ല. അതുകൊണ്ടാണ്. Okay. So is it clear? Okay, guys. So I hope it's clear. I think it's enough for today. So tomorrow we will catch up with the remaining sessions, like especially the concealed AC, cassette AC, and this vertical tower AC. So any doubts? No, isn't it?
Sir, there is one more equipment, some dryer filter or something.
Air filters?
Hello?
Tell me.
No, sir. Dryer filter, small component. Small
Dryer.
component, dryer, I think.
Dryer, which is also termed as to be strainer. Okay, now. Then one more thing you can actually see in something called as to be accumulator, which is placed in front of a compressor. Why? Because I told you from the evaporator, the mixture should be either in liquid or in vapor, isn't it? You know, there should be, it's not converted fully into vapor. Sometimes it should be some kind of liquids will be there or moisture will be there, isn't it? So I told you, sir, in the compressor side, if a liquid goes, what happens? It should ceases, isn't it? That's why we placing these accumulators. So this accumulator will drain up the moisture content right from the refrigerant right there itself. Okay, now. Okay, that's it. All right. Okay, guys. So I hope it's clear. So I'm going to wind up the session. So tomorrow we can catch up with the remaining topics. Okay, good to go, guys. Bye. Have a great day.